Good morning. Welcome to today's webinar, Giving Your Castings the Competitive Edge with Hot Isostatic Pressing. I'm Shannon Wetzel, Managing Editor of Modern Casting. We have a fantastic webinar for everyone with Magnus from Quintus Technologies. Before I introduce him, I want to go over a couple of housekeeping items. First, this webinar will be recorded and made available to today's attendees. You'll receive an email with a link within a week after the webinar. Second, Magnus will be answering questions at the end of the session. You may type your questions in at any time during the webinar in the Q&A tab on your control panel, and we'll get to as many questions as we can at the end of the session. Now let me introduce our speaker, Magnus Alfors. Magnus has worked at Quintus Technologies since 2013. As an application specialist for hot isostatic pressing, he is heavily involved in the development and optimization of HIP processes for different industries. Magnus has a master's in materials engineering from Chalmers University of Technology in Sweden. And since July 2017, he has been at the Columbus, Ohio Quintus Technologies location. And from there, I'll give it on to you, Magnus.
Thank you very much for the introduction, Shannon. Here we can see an outline of today's webinar. So first I will introduce our company shortly. Then we will go into the fundamentals of hot isostatic pressing HIP. Then I will cover the benefits of HIPping, the equipment used for hot isostatic pressing, and in the end I will cover something we call high pressure heat treatment and some case studies relating to that. So as a background, I first want to do a short introduction to Quintus Technologies. So here is our history of the company, and our operation started in 1940 when a department for high pressure technology was formed at ASEA. ASEA is a company that then became ABB that you might have heard about. And in 1947, ASEA started to look at how to produce synthetical diamonds. And in 1953, they were able to produce the first synthetical diamond, and this was done in a high pressure press that also can do high temperature. In 1964, the technology used to produce diamonds was then developed to make hot isostatic presses and cold isostatic presses, and these became commercial processes. In 1984, we invented the rapid cooling HIP furnace, and this allows a decreased cycle time and increased productivity of your HIP unit. In 2010, we built the biggest HIP system that still is the biggest HIP system today in the world. This one is situated at the company called MTC in Japan. In 2011, we took the rapid cooling technology a step further when we introduced the rapid quenching technology that can achieve very high cooling rates that enables in situ heat treatment into the HIP process. In 2014, we did a new design of HIP systems where we integrated all subsystems into one modularized solution. And since 2017, we have been owned by Kobe Steel of Japan. Today, we are around 240 employees worldwide. We have our headquarters in Västerås, Sweden, which is actually my hometown. We have a service sales office in Shanghai covering the Asian market. And then we also have a site in Columbus, Ohio, where I'm based, supporting the North American market. And our history of innovation have resulted in many patents, and what of 120 of those are still active today. And since the 1950s, we have developed over 1,800 high-pressure systems. Here we can see the main markets that we are working on regarding to hot isostatic pressing. So the aerospace industry is a big market for us. A lot of the components in the turbine engine are HIPped, for example, turbine blades. In the automotive industry, HIPping is used for structural parts, for example, cast aluminum engine blocks, and especially for high-performance cars and racing applications. In the energy sector, HIPping is used for nuclear components and also components for oil and gas. And in the same way hipping is used for turbine engines for airplanes, it is also used for industrial gas turbine for power generation. In the medical field, we have medical implants such as knee joints, hip joints, etc. And they often are hip because it improves the material properties and the reliability of those components, which is important. So now going into the technology of hot isostatic pressing. So there are a few different applications for hipping, and one of them is consolidation of powder. And this is where you produce a near-net shaped component or just billets by encapsulating a powder and hipping it to 100% dense material. And this is commonly done for stainless steels, tool steels, high-speed steels, but also other materials. Diffusion bonding is another application where similar or dissimilar materials can be bonded together in the solid state. So there's no melting in this process. And you can bond a solid to a solid, also clad a powder to a solid, and also do powder to powder compounds. The third main application for hipping is densification of products. This is commonly used for casting, additive manufactured materials, or sintered materials, any material that contains some kind of internal defects that can be eliminated. And this is the application that we will be focusing on today. So the definition of hipping is to apply a pressure distinctly higher than the yield strength of the material at the hip temperature. So it is a process with high temperature and high pressure. We can go up to 3,600 Fahrenheit and 30,000 PSI in the process. And at this high temperature, the yield strength of the material will be very low. So the pressure, the stresses that we induce in the component with the pressure will actually be higher than the yield strength. And as we know, when we have higher stresses than the yield strength, the material will plastically deform to, for example, collapse internal pores in castings. So the mechanism that's working during the process is mechanical deformation that I just explained. But we don't only want to collapse the pores, we want to completely metallurgically heal these defects. And that is where creep and diffusion comes in to completely erase these defects from the microstructure. And since creep and diffusion are time-dependent processes, that's why we have a soak time in our hip cycle. Isostatic pressure is when you have the same pressure acting on all surfaces in all directions on an object. And for the hip process, this is normally achieved by a pressurized argon gas as pressure medium. And here I want to show an example of what the hip process can do. So these are showpieces that were made to show the effect of hipping. So on the left here, we have two steel halves, and we have drilled a hole in each end of those. Those ends are put together and welded together, creating a cylinder with a big void inside. And then these specimens were hipped, and we can see the results here to the right. So these are cross sections of those samples, and the sample on the left here is a reference, so this has not been hipped, and we can see this big void inside this half cylinder. The specimen on the right was exactly the same specimen like this, but then it was hipped. And as we can see, we were able to eliminate this huge pore with the hip process. And since the pore is relatively large towards the sample size, we can see that we also get some macro deformations on the sides here. Here's an example of a real casting porosity microstructure. So here we can see some typical casting porosity, and these type of defects can also be eliminated by the hip process. One thing to notice is that it is only the internal defects that are eliminated with the hip process. Any surface connected feature where the pressure media can penetrate will not be affected by the hip. So for example, a surface crack like this, the pressure media will just go into the crack and there will be no net force to close that crack. Also, a rough surface will not be affected by the hip process. So a gas-tight surface of the component is a requirement for hipping, and this is normally not an issue for castings, which is a good thing. The shrinkage we get in the process corresponds to the amount of densification we achieve. So if we, for example, have 1% porosity, and we hit in a material and we hit that to 100% density, we will get a shrinkage by volume of 1%. And 1% shrinkage by volume, that corresponds to 0.33 linear shrinkage in each direction of your part. So it's not a lot shrinkage in the process. Here we're going to go through some of the typical HIP cycle parameters used. So the HIP temperature is normally around 80% of the melting point. That is the solidus temperature of the material. The pressure is normally ranging between 7,000 and 30,000 psi for castings. This is somewhat depending on the strength of the material. So, for example, when I HIP ceramics in our lab here, I normally go with the highest pressure. The soak time in the process is typically between 1 and 4 hours. Most metals are sufficient to have a 2-hour soak time and get full densification. However, when we look at materials that are designed for high temperature creep resistance, for example, the nickel-based superalloys, titanium aluminide, etc., in those cases, we tend to go to higher soak times, longer soak times, such as 4 hours, since high temperature creep is pretty much what we're trying to achieve in the HIP process. And the main purpose with the HIPing is to achieve 100% density to eliminate all the defects. And there will be different combination of time, pressure, and temperature how to achieve this state. So there's not one unique cycle per alloy. So there will be different options, and whichever of those options is the best might be determined by other factors. So, for example, say that we want to minimize the grain growth in our process, then we would choose as low HIP temperature as possible and as short soak time as possible, and we probably have to compensate with maximizing the pressure. Another example is if we want to avoid or promote a phase transformation to happen during the HIP step, then we would adjust our HIP temperature according to that. And also it can be just process economy. Maybe we want just a cheaper cycle that will achieve the 100% density of our parts. And now I want to cover some of the benefits with hot isostatic pressing. And as cast material typically have some internal defects, such as shrinkage porosity due to the volumetric change during solidification. Also, gas porosity is pretty common due to the decreased gas solubility when the melt starts to cool and solidify. And what these internal defects do is that they will act as stress concentration and crack initiation points in the materials. And that can negatively influence your material properties. So the main purpose of HIPing is to eliminate these defects. So we eliminate the stress concentration and crack initiation points and get improved material properties. And the typical material property we see improvement of is ductility and fracture toughness, better creep properties, and especially improved fatigue properties. Since we have a natural variation of porosity, like in the amount and the size and the shape and position of them between different castings, we will also see a variation in properties. But since we're eliminating these defects with the HIP process, we typically see a reduced scatter of the properties with HIP. Also, HIPing can also be used to improve the quality of machine and polished surfaces. And this is since there's no internal porosity that can appear in that surface. And this is important when it comes to corrosion properties, optical properties, and aesthetical properties. So, for example, HIPing is actually used within the jewelry industry, where they HIP pressure metal castings to be able to achieve very perfect surfaces, because that is a requirement in that industry. So they don't use HIPing for the mechanical properties, they just use it for aesthetical properties. To have good machine and polished surfaces is also important for sealing applications, of course. And here we have an example of the typical effect of fatigue, typical effect of HIPing on the fatigue properties. So on the diagram here on the right, we see fatigue data for a cast aluminum alloy, A206. And this is a material that's been cast and then heat treated with a T71 treatment. We have variants with and without HIP. There were 10 specimens per condition that was tested and at one stress level at 24 KSI. So we can see the number of cycles to failure here on the y-axis. And there on the left here in green, we have the material that has been cast and then heat treated, so no hipping for these. And here we can see that the specimen that produced minimum amount of cycles were around 6,000 cycles, and the average life was around 21 to 22,000 cycles. On the right here in blue, we have the same material that's been hipped and then T71 treated. And as we can see here, the minimum value is over 200,000 cycles, and the average life is around 2 million cycles. So here we can see that we get over 30 times higher minimum value with hipping and over 90 times higher average value with the hip material. So this is one of the main reasons hipping is used for castings. Here's an example of the improved machine surfaces with hipping. So on the left here, we have a cast tube that's been machined the inner surface. And as we can see, we have revealed quite a lot of internal porosity in that surface. So this is, of course, not optimal. On the right here, we have the same type of cast tube that's then been hipped before it was machined. And as we can see, we have a virtually perfect surface. So that was the more technical benefits of the hip process in terms of mechanical properties, etc. But what are the outcomes of these in terms of a business case, for example? What are the drivers for using hip for castings? So the improved material properties with hip, that allows us to use higher stresses in our components. And this gives that we can use lower weight designs. We can use less material to produce our component to get the same properties, the same performance, the same service life. Also, the reduced property scatter, that gives us a more predictive material properties that hopefully we can use design values closer to the actual strength of the material. So the engineering safety factors we use in dimensioning, we could probably reduce a little bit. So this also makes it possible to design a lighter component. And a low weight design is of course important in today's industry, since there's a lot of fuel saving goals, etc. And the high quality and performance of a final part is important, for example, to avoid the component failure in an application, which can be very costly, and also it can have some big consequences. So the most extreme example is probably the turbine engine in an airplane, for example. But also for less critical application, it's important to have that high quality. And I also believe that a high quality and performance of cast parts it's really important to stay competitive towards emerging technologies. For example, metal additive manufacturing, which is growing very fast, have been for the last couple of years and will continue to do. That process is starting to compete with castings more and more in different areas. More outcomes. So very common in the casting industry is of course to use non-destructive testing such as X-ray analysis to make sure that the internal porosity is within allowable limits. But since we're eliminating these porosity with the HIP process, it might be possible to reduce the non-destructive testing or even eliminate that part of the process chain. And this will of course save cost. In the same way, if we don't have any porosity that can be outside of the spec, we can also reduce the scrap rates for our casting. And this is very good since we don't have to remelt, recast, and re-NDT components. The improved quality of machine and polished surfaces, that makes it possible to avoid part leakage in sealing applications. And also, it's very annoying to find surface porosity during final machining of a part, where all that value-adding work that you put into the component at that point is just flushed down the drain when you have to reproduce that component. So all of these points make a potential to lower the production cost in the casting process chain. So with increased quality and high performance by HIPing and also a potential cost saving, this is how HIP increases the competitive edge. Here I want to talk about an interesting approach that we have successfully tested for additive manufactured material, and that is to allow a higher percent of porosity in the as-cast condition, or in the as-printed condition in that case. So hipping will give you 100% density of the material independent of the starting density. So to the hip process, it doesn't matter if you have 1% or 5% porosity in your casting. It will still be 100% porosity density in the end, as long as the parts have a gas-tight surface, which they have. So if we know that we're going to hip, or that we decide that we're going to hip, we could allow a higher amount of porosity in the casting, in the as-cast condition. And this could open up some possibility to simplify the casting process. For example, maybe a more simple casting method could be used. It might be possible to reduce the need for sophisticated simulation and process control tools, less requirement on the cleanness of the melt, and the simplified mold design, etc. So here we have another potential to reduce cost in the casting process by hip. Now I want to cover the sourcing of the hip process. So there are mainly two ways to acquire the hip process today. Either you buy the service from a hip service provider, where you would ship your parts to a site, get them hipped, and ship back. And the other alternative is to have the hip operation in-house. If we look at the hip service provider, this is a cost-effective alternative, and especially for smaller production volumes. The hip service provider often run coach cycle, which means that they take components from different customers and they run it together in one cycle. So you kind of share the cost of the hip process with other parties, which makes it cost effective. Also, of course, no hip know-how is needed, since the service provider knows exactly how to treat the material in a good way. And of course, no capital investment is needed if you buy the process. And talking about the hip service market, there will be 3 new hip service providers in 2019, in addition to the already existing ones. And one of them is a company called Paolo. They will get a medium-sized hip to their site just outside of Cleveland, Ohio. And this hip system will have rapid cooling capabilities and high-pressure heat treatment capabilities. And they will offer hip and heat treatment services from this one site in Ohio. Another company is Stack Metallurgical Group. They will get a large hip system to their site outside of Portland, Oregon. They have a good experience in castings, and they will also provide hip and heat treatment services out of this site in Oregon. And the third company is Heat Treatment Mexico, which is based down in Mexico. They will have a small to medium-sized hip that they will use for hip and also heat treatment services from one side. So we're pretty excited about these 3 new hip service provider, because it gives the customers more options on the market. Looking at having the hip process in-house, that also have some benefits. And first of all, it gives you the lowest cost. For example, there will be no markup from the service provider, of course, and also no shipping is needed to any other site, which will, of course, eliminate the cost for that shipping. But it also shortens the lead times, which will decrease your working capital for a better cash flow. You also have full control of the process. You can plan and schedule exactly when you have to have the hip cycle done, and you don't have to wait for a hip service provider to do it. Also, since you're not restricted to the standard cycle of the service providers, you have the possibility to develop optimized hip cycles for your material and your application for the best performance. Now I want to cover some information about the equipment for hot isostatic pressing. And here we can see the different building blocks of a modern hip system. And in this picture, we can see a hip system with integrated subsystems in a nice modular solution. So we have our pressure vessel, and then inside the pressure vessel, we have the furnace. And the furnace is powered by a power module, and the pressure vessel is also cooled with an internal cooling system. And that internal circuit is cooled with an external cooling system. Then we have a gas storage, which contains the argon gas used for the process. And the argon gas go through a gas module, which will pressurize the gas to generate the high pressure in the process. And this is done with one gas compressor or several gas compressors. There's a hydraulic system as well to create the movement, for example, moving the frame back and forth for opening and closing the system. And also the hydraulic systems are driving the gas compressors. There's a vacuum system, so we can evacuate the air from the system before we start running a cycle. And there are some important considerations for building a hot isostatic press. And first of all, we have the pressure vessel design, which is important because that is related to the safety of the system. At Quintus Technologies, we use wire-wounded pressure vessels, and we have a schematic picture here of our wire-wounded cylinder. So we have a relatively thin-walled forged cylinder that we put a lot of wire on it with force. So we actually pre-stress this cylinder and squeeze it together. So this inner diameter of our pressure vessel will actually decrease during the winding of it. And this creates compressive stresses on the inner surface, and this prevents crack initiation and growth for safety reasons. So even at maximum operating pressure, there will be only compressive stresses in the forged cylinder. Another consideration are the safety systems. So there will be oxygen sensors in different parts of the HIP system to pick up any potential argon leak. There are pressure gauges and pressure relief valves in the HIP system, in different parts of the system, and this is to have a controlled discharge of pressure in the unlikely event of an overpressure for some reason. There's also door supervision and protection covers. For the larger HIP systems, there are automatic evacuation fans also for any unlikely argon leak. And thanks to the wire wounding technology of our pressure vessels, we have the possibility to have cooling channels quite relatively close to the hot zone. So in this schematic picture here, we can see our forged thin cylinder, and then outside of that, we have our wire wounding, and then in between, we can have our cooling water. And this effective cooling we have enables us to perform rapid cooling in the HIP system. And the rapid cooling is important because it shortens your lead times, shortens your cycle times for increased productivity that gives you the best process economy. Here's some details about the HIP furnace. So HIPPing is a batch process, and this is because of the high pressure we have. So during the cycle, the system has to be closed, and we can only open the system in between cycles due to the pressure. We have a vertical cylindrical hot zone where components are placed on different load trays on different levels and load baskets. We can see a schematic picture here on the right. And this load basket and component assembly is built outside the HIP system, and then this whole assembly is lifted into the HIP furnace with a furnace tool. There are some different furnace materials available depending on your application. So we have molybdenum furnaces that goes up to 2700 Fahrenheit. These can process most metals with those temperatures. But then we also have graphite furnaces that goes up to 3600 Fahrenheit for high temperature ceramics and refractory metals. Since we have a high pressurized argon in the HIP process, that gives us a very high conductivity of the process gas, and that gives us a very good thermal accuracy and uniformity. So we're typically within plus minus 3.6 Fahrenheit all over the hot zone, in the entire hot zone. Here we can see an example, well, the range of sizes of commercially available HIP units today. So Quintus Technologies, we have one small production units collection. which has a diameters up to 14.7 inch, and they can go up to maximum temperature, and these systems can achieve up to 8,000 Fahrenheit cooling rate per minute, which is very fast. Then we also have mid-size production units with hot zone sizes up to 41.3 inch diameters. Also max temperature and cooling rates up to around 390 Fahrenheit per minute. Then we have large production systems that is up to 81 inch diameter. This is the biggest one we have ever built, but we can build bigger if needed. These goes up to 2,500 Fahrenheit and have these also have slower cooling rates. And these very large systems, they can take up to 60,000 pounds of components per cycle. Now I want to talk about something we call high pressure heat treatment. So historically, HIP systems had very slow cooling rates. The cooling was achieved just by shutting off the furnace and letting the system cool down by itself. And that could take many, many hours. So conventionally, heat treatment was not possible to do in the HIP process because of these slow cooling rates. They were not high enough to heat treat materials with good results. However, modern HIP systems of today, they can achieve very high cooling rates. So this makes it possible to perform in situ heat treatment in the HIP process in one cycle in the HIP system. So today, HIP system can not only be used for defect elimination, but also to modify your microstructure for desired properties. So here we can see a typical post-processing route in the conventional way. So for a cast component, we might have a HIP step first with a slow cooling. And then after that, we have probably some kind of solutionizing step with the quenching. And then we might have an aging or tempering step after that. And the main purpose with high pressure heat treatment is to reduce the number of process steps. So these conventional steps can be combined into one cycle to be performed in one equipment, the HIP. This will, with this combination of steps, you can reduce the total processing time, and also since we're reducing the downtime between the processes, we can reduce the lead time. Sometimes these processes, HIP and heat treatment, are done at different sites, and then you need shipping in between these steps, which takes a lot of time. Also, since we're heating up the material less times, we can reduce the energy consumption. And from a material standpoint, in this case, we might have a soak time in the HIP cycle of 2 hours, and then a 2-hour soak time during the solutionizing step. And of course, if we combine these two steps together, we only have 2 hours at temperature instead of 4 hours at temperature. And this can be quite important when it comes to minimizing grain growth, for example. And here we can see an example of high pressure heat treatment. So this is for a cobalt chrome material, and this specification I've taken from a material supplier website, and this is actually Arcam's website, so it's a 3D printing company website, and but it makes a good example. And here are the recommended post-treatment of their cobalt chrome parts. So first, they recommend a HIP cycle at 1200 Celsius at 100 megapascals for 4 hours. And then after the HIP step, they recommend a homogenization step at very similar temperature in vacuum, also 4-hour soak time. And then they have a requirement on the cooling rate. And this required cooling rate corresponds to 105 Fahrenheit per minute. And the purpose of this is to avoid carbide formation in the material during the cooling. So 105 Fahrenheit per minute is easily achievable in a modern HIP system. So it would make very much sense to combine these two steps together to do one cycle in one equipment and spend 4 hours at temperature instead of 8 hours at temperature. And it's not only the cooling, a fast cooling rate that can be achieved in a modern HIP system. It is also a very flexible type of heat treatment. So you can build your heat treatment recipe with the infinite many heating, soaking, cool, quenching steps, etc. We can see an example here. So this is actual log data from a hip cycle where we have combined the hipping and the hardening for a tool steel. So here we increase the temperature and the pressure as a normal hip cycle. We have our typical soak time, and then we increase the temperature just a little bit before quenching down to room temperature. And then here we have a 3-time tempering as well for this particular material. So it's a very flexible system to do heat treatments in. Some of the benefits with high pressure heat treatment. One thing to notice is that the high pressure in the process remains during the cooling and quenching. And since we have this high pressure gas, we also have a very high density in the gas. And this gives us a very high thermal conductivity in the pressure medium. And this gives us a very high heat transfer between the components and the process medium. And this is very good when it comes to heat treatment. Also, we have the components and the pressure medium starts at the same temperature when we are performing our heat treatment. So we start cooling the pressure medium, and then the components will follow. So it's a little bit softer quenching compared to a water or an oil bath quenching, where you have this initial thermal shock in the beginning. So with this process, we get low thermal gradients, low thermal stresses, and a low risk of crack and distortion during the quenching of our parts. The hip furnace is just one chamber. There's no heating chamber and quenching chamber. Everything is done in one chamber. So there's no movement of the parts during the process. And this makes it pretty easy to monitor the temperatures during the cycle. So this is a setup in our smallest furnace in our lab in Sweden. Here we have a relatively large sample compared to the furnace. And here we can see that I put thermocouples in the gas around the component. I have one thermocouple on the surface of the component, and I've also put one thermocouple in the center of the component here with this drilled hole. So it's very easy to monitor the temperature in different parts of your component for process validation and research, etc. So you know exactly what cooling rate you had in different parts. Also, since we're performing the heat treatment under pressure, there's no risk of thermal induced porosity or blistering of your casting. And here are some examples of common materials suitable for high pressure heat treatment. So we have our steels, which are stainless steels. We can have the 17.4 pH precipitation hardening steel. We have stainless steel 420, martensitic hardening steel. We have tool steels, more aging steels, duplex stainless steels. Also aluminum alloys, they're typically age hardening, can be produced. The nickel-based super alloys are common for age hardening. For example, Inconel 718, Inconel 738, and Vaspalloy. And then we have titanium alloys such as Ti64 and also intermetallic titanium aluminide. And now I want to show a case study for high pressure heat treatment, and this is the effect of high pressure heat treatment on creep properties for nickel-based single crystal casting. So this study was performed by Ruhr University of Bochum in Germany. This university have a HIP system from us with the very fastest quenching capabilities. And they were looking at a single crystal alloy called Erbo 1, which is a similar alloy to CMSX4. And in this study, they looked at two different variants. They looked at material that was heat treated in the conventional way in a vacuum furnace. And then they also looked at the combined HIP and heat treatment step for this material with rapid cooling in the HIP. And then the density, microstructure, and the creep properties were evaluated. So here we can see the parameters for the conventional heat treatment. We have a solution annealing for 6 hours, then we cool down to room temperature, and then there's an aging first at the higher temperature for 4 hours, and then at the second temperature for 16 hours. And the cooling rate that was achieved in this gas quenching vacuum furnace was around 270 Fahrenheit per minute. We did the same type of treatment in the HIP system, with the difference that here we have the pressure at 15,000 psi. And also the cooling in the HIP system were around 2,700 Fahrenheit per minute, so much faster cooling than in the vacuum furnace. And we can see the log data from the combined HIP and heat treatment cycle here in the diagram to the right. So we have our solutionizing, cool down, first aging, and then second aging. And here we can see the results in terms of porosity. As expected for the heat treatment only variant, we still have the casting porosity in there. It's around 0.25%. And the HIP and heat treatment variant, we can't see any porosity here, which is also expected with the HIP process. Here we can see the results in terms of the microstructure. So we have the conventional heat-treated variant on the left and the combined HIP and heat-treated variant on the right. And both variants have the same gamma prime volume fractions, around 75%. But we can also see a difference here that the gamma prime microstructure for the combined HIP and heat treatment cycle is much finer. And this is due to the faster cooling in the HIP after solutionizing compared to the cooling in the gas quenching furnace. And here we see the results of the creep properties. So they tested two different conditions, one with a lower temperature and higher stress, and one with a higher temperature and lower stress. And in both cases here, we can see that the HIP variant have a higher, longer creep life than the conventional heat-treated variant. And this is due to the elimination of the cast porosity in that material. We can also see, looking at this graph, that the HIP and combined HIP and heat-treated variant have a lower minimum creep rate than the conventionally treated material. And this is thought to be due to the finer gamma prime microstructure achieved by the higher cooling rate in the HIP. Another case study here is for a combined HIP and T6 treatment, an age hardening for an aluminum alloy. And this study was done together with the Technical University of Munich in Germany. Here we wanted to see if we could incorporate the T6 treatment into the HIP process for a cast A356 material. And the purpose of this is to reduce process steps in your process chain. And the question is if we could achieve the same material properties with heat treatment in HIP compared to a conventional heat treatment with water quenching. And in the matrix down here, we can see the different variants. So we had one as cast variant, we had a variant that was cast and then conventionally heat treated with water quenching. Then we had a material that was conventionally HIP'd and then afterwards conventionally heat treated with water quenching, the full heat treatment. And the fourth variant was a combined HIP and heat treatment where we performed everything in the HIP. And we can see the log data here from that HIP cycle where we have our combined HIP and solutionizing step, then we quench down to room temperature, and we also do the aging in the HIP. And here we can see some info of the process parameters. The testing that was done was tensity measurements, hardness measurement, tensile testing, and fatigue testing. And we can see the results in terms of density here on this diagram. And as expected, the two HIP variants have a higher density than the two that are not HIP. Here we see the results in terms of yield strength and hardness. And conclusions from this slide is that the strength and hardness is higher for the heat-treated variants compared to the as-cast variant, as expected. And we can also see a little bit lower strength with the combined HIP and heat treatment variant compared to the conventional heat-treated variant. And the reason for this is that the cooling rate in this HIP we used for this trial will be a little bit slower than water quenching. So we can see the cooling rates that we achieved in these materials, in these specimens for that HIP cycle. However, this study was performed 5 years ago, and since then we have developed our furnaces even further. So today we can achieve significantly higher cooling rates than this. So I believe if we would redo these trials, we would get this strength up a little bit. And here we can see the UTS and elongation. We get better UTS as expected for the heat-treated variants, and the ductility is significantly higher for the two variants that are hipped compared to the as-cast material and as heat-treated material. Also, as expected, we see better fatigue properties for the variants that have been heat-treated, and also the hipped variants here are higher than the just heat-treated variant. Interesting here was that we actually got better fatigue properties of the combined hip and heat treatment variant, even though it had a little bit lower strength than the conventional hip and heat treat variant. That was pretty much it from the technical part of this webinar. So now I just want to give you some information here. So as Shannon already mentioned, there will be recorded versions of this webinar. It will be sent out as a link, but it will also be available on the Quintus Technologies YouTube channel, and our name on YouTube is just Quintus Technologies, and those will be available around 1 week from now. And then I also want to mention that we will be at the Quintus team, including myself, will be at Cast Expo trade show in the end of this month. We will be in booth 1845. So you're very welcome to combine and talk to me or any other in our team about hipping. And it is also possible to book a meeting beforehand in case you want to have a more separate discussion. So that can be done by emailing this email address here. And by that, I thank you very much for your attention today. So I think we're now ready for some questions and answers.
Thank you very much, Magnus. And again, everyone, you can go ahead and put in your questions. We'll answer as many as we have today in the next 10 minutes or so, and then hopefully what doesn't get answered, the team at Magnus can follow up with via email. So first we'll start off, Magnus, with a question. Someone asked that you highlighted that a gas type casting is required for efficient hipping. However, some casting alloys contain surface-connected shrinkage porosity. They refer to the 200 series. Is there any development going on in the industry associated to closing surface connect porosity as a prior process to hipping?
Yeah, that is true, that if your porosity is surface connected, it will not be eliminated by the hip process because the argon gas will penetrate that feature. And we haven't worked with any improvement to or process to close those before the hip cycle. But I mean, welding is used to close those before hipping. But personally, I haven't worked with that process at all.
Okay. And then we had a couple of questions about ferrous material being going through the hip process. One asked about carbon and chrome moly steels, and another one asked about gray and ductile iron, if there's a reason why those weren't mentioned, if it's too expensive, or if there's a technical reason why.
Okay, yeah. So the slide I showed some materials that were common materials that we have worked with for the combined hip and heat treatment, but there's a lot of other materials there that are hipped and also potentially heat treated. So steels, the ferrous material that you mentioned, can be hipped, and also cast irons is also hipped. So the hip process doesn't really care about the material too much. It's the gas tight surface and just that it's a metal that you can heat up, I guess. So anything from magnesium to high temperature ceramics can be hipped.
All right. What does the post-hip process surface finish look like? Does it get discolored and oxidized? Does it need to be shot blasted clean? Return to the typical surface?
Yeah, so the surface roughness is not affected at all by the hip process, and the surface appearance, it depends on what alloy you're working with and how you're doing your hip process. If you have materials that have a high affinity to oxygen, for example, titanium or a stainless steel, you have to take care about your hip process, how you treat your furnace, what your process gas is, because there is a potential for oxidation of the parts if you're not operating the process in the correct way. So it's going to depend, but yeah, it can be some oxidation of the parts.
All right, thank you. You also in your slides showed some HIP service providers in the U.S., and there was a couple questions about if there are locations in the UK or Europe that provide the service.
Yeah, there are definitely HIP service providers in Europe and in the UK, yeah, Bodycoat is present both in the US and in Europe. That's one of the biggest one, but yeah, I don't know too much about the HIP service market in Europe, but there are definitely different companies there, and we know all of them. Maybe not me personally, but Quintus do. So they can contact us for some different names of service providers.
Okay, thank you very much. I'm scrolling through some other ones now. Do you have any data for improved fatigue life? They're asking for cobalt chromium molybdenum alloy, but just in general, if someone was looking for improved fatigue life data, is that something that Quintus has, or is it available?
Yeah, we have a little bit of internal data, and then there's also, publications on it. The slide I showed with the improved fatigue properties, that's from a paper. So we definitely have a database with all the papers that we have found over the years. So yeah, that's also something that I could be contacted for to to recommend some papers for different materials. Cobalt chrome specifically, I don't know if we have data on it or not, but for different materials we do, yeah.
All right. Another question is, do you have a guideline cost calculator to treat per pound of material for the cycle required? Or is there something for a general direction of how to kind of figure out the cost?
Okay, yeah, we do have an internal tool to calculate the process cost of hipping based on, the production volumes and the size of the parts, what material of the parts. We can figure out what type of hip system size would be needed, and then based on the material and the cycle, we can calculate and a lot of how they're processing and etc. We can calculate the cost of the hip process per pound or per part. We don't have that available as a tool we can send to people. And of course, when you go to a hip service provider, I mean, it's going to be the price depending on the lot size, etc. But that we do calculations like that. I wrote a paper 2 years ago on the cost of hipping that I could send for that explains kind of how what variables are affecting the hip process cost and also how to calculate it.
All right, we have a question about applications. You mentioned joints in the medical field use the HIP process or have the HIP process used on them. Are there any other medical field applications that you can think of that would use this process?
Yeah, I guess any type of implant, and also I mean, I know implants for teeth, those are mainly 3D printed or MIM components, so not really casting, but they are typically hipped. And there's other dental application like braces components, etc. So they're definitely mainly the implants that go into the body and stay there. For example, plates and screws that are just temporary in the body to fix a fracture, for example, those probably don't need to be hip because they don't have to have the long service life. But pretty much anything you put in your body is hip, because it's of course very inconvenient to having to replace a joint because it broke. Yeah.
Thank you. I'll probably have time for just 2 more questions. The second to last question is, would section size have any effect on the process?
No, not really. So like, yeah, the component size, the thickness of a component or wall thicknesses, not really. So for really, really bulky parts, like really big castings, you might add a little bit of soak time to the HIP process, since it takes some time for the heat to travel from the surface into the center of the component. But besides that, it doesn't really matter if you have very small components or large components. The process parameters look pretty much the same.
All right, and then our final question for today was about like an application like an engine block. I don't know how well you can answer what would be the cost of hipping something like an engine block.
Yeah, that depends a lot. I don't know the exact cost, and if you have one engine block that you want to have hipped, it's probably gonna be expensive. If you have like a full production of engine blocks, so you can fill up a hip, then it will be not very much adding cost to it. I know my colleague wrote a paper where he calculated for a big hip system that you can run every day, fill up and run every day, the costs are in the order of magnitude of 10 cents per pound for in-house production.
Great, thank you so much, Magnus, for a really great presentation and for being gracious enough to answer some of those questions for us. And thank you all to the attendees for joining us today. And if we didn't get to your question, we'll try to get to that within the next few weeks. And then we'll also be sending a link to the recorded webinar next week, so you have that to reference and to pass along to your colleagues. And again, thank you, Magnus, for joining us, and thank you to all our attendees.
Okay, thank you, Shannon, and thank you all for listening.